So now we move on to decimals instead of just fractions. So if it's been a long time since you've worked with fractions, you probably had the urge to convert things to like percentages or decimals when we were talking about things. In fact, when I went over that Boston to New Hampshire, that Boston, New Hampshire question, I converted it to a decimal because it was 2.5 hours. And so I said 2.5 instead of 2.5. So the goal of this chapter is to understand the process of decimal conversions, rounding, the difference between the whole number section and the decimal section. A lot of this will be probably straightforward, but it's important to make sure that we're all on the same page. And then the real kind of meat of this lecture is just kind of doing basic arithmetic with decimals, adding, subtracting, multiplying, and dividing. Decimal conversion is not too difficult, especially if you're going by scales of 10, because if you're going by scales of 10, since we use a base 10 system, it becomes pretty easy to like just kind of move the decimal point into one direction or the other to change the value. And then it'll be doing our basic adding, subtracting, multiplying, and dividing. That will kind of be the focus. So I don't have another thing of M&Ms. I don't have another bag or another box. I have a half of a Snicker bar, but that's about it. So this is not the data that we collected last week. This is actually data from the textbook where if they had a bag of 50, they had 55 M&Ms in it, and there were 18 yellow, 10 red. I'm going to sneeze, so 1 second. Sorry about that. I think I muted myself to spare you. So we had 18 yellow, we had 10 red, we had 9 blue, 7 orange, 6 brown, and 5 green. That seems way different than what we got last week. So if we converted this from a fraction to a decimal and rounded to the nearest hundredth, so again, the first place at, so again, remember every numerical scale that you have is by tens. So when you have like a whole number and then you have a number next to it, well, then that's tens and that's ones. But when you go to the other side, it's the opposite. It's tenths, hundredths, thousandths. So when you see two numbers after the decimal sign, that means we're in hundredths, 3 thousandths, 4 ten thousandths, 500 thousandths, 6 millionths. And then on the left-hand side, it's 1, 10, 100, 1,000, 10,000, 100,000, 1 million. So how do we get this? Well, the easy way that we've all learned is through our calculator, where if you did 18 divided by 55, you get 0.327. 0.327, and then you would round up to the next hundredth. So if the rounding rule is if it's greater than or equal to 5, go up. If it's less than 5, so 4 or below, you round down. See, I think it disappeared for a second because it said that you could see it now. I'm going to stop it and restart it. Thanks for bringing that up, because like for some, I shared it and then it said the participants can now see it, but can you see it now? You can put a thumbs up in the reactions or something if you can see. Cool. So I didn't know if you could see this before. I apologize if you couldn't. So we had 18, 10, 9, 7, 6, 5, and then we add them all up. So if you just put this into your calculator, did 18 over 55, you get about 0.327. Since 7 is greater than 5, you get 0.33. And then 10 over 55 rounds to about 0.18, 0.16, 0.13, 0.11, 0.09. The thing that you should notice is, just like last time, the sum of all of these should equal a whole number. And then the sum of all of these decimals should equal 1 as well, because 1 represents the entirety of the whole of the bag. What I wanted to do is I wanted to use our own data, since we did this collection last week, and then convert all of this to a decimal. Now that we've done the fraction piece of this, we can take this one step further and then try to the decimal value. So if you do 13 divided by 105 in our calculator, we get 0.1238. If I wanted to round this to the nearest hundredth, what would I put? Would I put 0.12? Would I put 0.13? How would you round this to the nearest hundredth? Remember, hundredths are these two right here.
It'd be 0.12.
Does everybody agree with that? I see agreement in the chat, at least one concurrence. And I agree as well. So it's kind of interesting because we're at 0.38. So if you do the round rule here, you round up to this up. So this becomes 4, but 4 is still less than 5, so you would round down. Sorry, that's not a good down arrow, but. And I'm just shortcutting by using the calculator here for these. I'll just show you basic division in a bit with these, with numbers and decimals in a second. But so we've decided to truncate this down to 0.12. Now if we go to blue, 22 divided by 105 is going to give us 0.2095. So would this be 0.21 or 0.20?
0.21.
Right. Because this rounds up to 1, this rounds up, and this rounds up. So we end up with 0.21. 17 divided by 105 is this going to give us yellow and brown's respective numbers. So when we do 17 divided by 105, we're going to round the same way for both. We get 0.1619. So up or down on that one? 0.16 or 0.17? So Bethany says 0.16. 0.16. So yes. 0.16, good. And then the same is going to be true for our brown, because we have the exact same fraction. Now 1/5 is easy if you're familiar with the ratio. If you divide 100 by 5, you get 20. So that means that this is 0.20, and there's nothing after that. In fact, you could even just leave it at 0.2. But if you want to round it to hundredths, you get 0.20. And then lastly, we get 1 divided by 7. So when you do 1 divided by 7, you get 0.14285. We'll just do 0.1428. But I wanted to use green. Yes, it's going to be 0.14 once we round. Oh my goodness. Work. There we go. So we have that, and then we add all these up, we get 0.33, this is 0.33, 0.49, 0.65, and then we're off by 1 because we rounded down 3 times. So we ended up with 0.99. We're missing 1 because we rounded down, or this didn't have any rounding. We rounded down, rounded down, rounded down, rounded up, rounded down. So if we think about it, this one was like close. And then I think this one, well, that was 2.8. Just say this one was close, and then we'll make it 1. So the rounding rules are fine. So even though this gave us 0.99, that's fine. Generally speaking, if you're playing games with like probability and fractions, you would probably extend it beyond the hundredths to make sure that you don't have a missing hundredth. But for most cases, especially in this class when we're going to be focusing on business type problems, we're going to be thinking about dollars and cents. This is about as far as it goes. Does anybody know what cryptocurrency is? Bitcoin, things like that. Anyone heard of that before? Yes, no, maybe so.
It's
I'm not gonna
real money. It's like on the internet, isn't it?
So it depends on what you define as money. So some of you might take macroeconomics with me someday. If you need to take Econ 101A for your programs, I'm the econ instructor, so we'll talk about money a lot someday. And money, as we perceive it, is physical dollar bills, coins, pennies, things like that. And in other countries, it's their own respective currencies like euro and yen and yuan and stuff. And we think about it in like just a vault full of cash at banks and stuff like that. But the reality is that money really can be anything so long as the general population adopts it as money and treats it as money. So just because Bitcoin, all these cryptocurrencies are digital and not physical, most of the money you deal with on a daily basis is digital anyways. These days, if you use credit cards and bank cards and things like that. But yes, it's not abundantly clear whether cryptocurrency is money because is it an asset? Is it money? But that's not really what the debate I wanted to have here was. I just wanted to mention it because we're so used to hundredths. We're so used to things being divisible by 100 in terms of our dollars. What if I told you the US dollar was not divisible by 100? What if I told you the US dollar was divisible by 1,000? Would you agree? Would you disagree? Have you ever seen a place where the dollar has been divided by 1,000? I'm sure you have. I'm sure you've seen it all the time that a dollar has been divisible by 1,000 instead of 100. Now, when you buy something at the grocery store, you typically don't. They'll round up or down based on the penny. But where's a place where a penny gets broken into tenths again? Anybody know? Two people said the gas station. Exactly. If you've ever focused on a gas station price tag, you'll see it says, okay, like two, I'll use red, $2.99. So you're like, okay, it's $2.99. But then there's this little 9 at the top of it. So and that 9 doesn't stand for to the 9th power, because if it was, then that would be the most expensive gas you'll ever buy, because that would basically be, oh my gosh, what is 3 to the 9th? Oh, 27 cubed. What's 27 cubed? I don't even know if I want to know. 27 times 27 times 27. That means if it was 299 to the ninth power, that mean that 1 gallon of gas would cost you $20,000, basically $19,683. But that 9 is not an exponent. It's just basically a little symbol that says that you're paying 9/10 of a cent. So you're really paying $3, not $2.99. And the reason why they do this, they work on thin margins with the gas. Their profit margins come from the convenience store attached to it. And now the advertisements that they sell on that annoying screen, and when you fill up your gas tank now. So they're trying to squeeze an extra 9/10 of a cent out of you without you noticing it, and also being competitive with everybody else. So gas station always has no problem dividing your prices by fractions of pennies. The reason why I bring up cryptocurrency is cryptocurrency technically is infinitely divisible, and I guess dollars are too, but it's too cumbersome to do that. But generally, Bitcoin, at least as an example, is divisible by, I think, 10 to the negative 8th or 9th, which means that when we play this decimal game, if you see 10 to the negative 9th, what that means is that if you take 10 and you move the decimal place over 9 spots and you fill it all with zeros, that is the divisibility of 1 Bitcoin. So you can make it really small, you can make it really scaled up. And so one of the benefits of the digital is that you can make it a really, really, really small decimal value. So like Bitcoin as of today is worth $47,000 for one of them. Most people can't afford a $47,000 digital coin, so they buy tiny little fractions of it. So I own some Bitcoin, but I don't own a whole Bitcoin. I tried to buy a whole Bitcoin when it was at $3,000 last March, but I was only getting paid once a month. And so it shot up and doubled in price overnight the day before my paycheck showed up, or else I'd have an extra 50,000 in the bank right now, but instead I don't. I don't know if anyone else has experienced that, learned about it, but I just wanted to talk about it in the context of decimals. So as I was mentioning before, the decimal point is the divider between whole numbers and basically fractions. So if you are the first digit to the left of the decimal point, that's just ones. If you're to the 2 to the left, you're tens. 3 to the left, hundreds. 4 to the left, thousands. Lots of us are used to that. And then every 3 you add, and then every 3 you add a comma. So 10,000, 100 billion. 10 millions, 100 millions, billions. 10 billions, 100 billions, trillions. 10 trillions, 100 trillions, quadrillions. 10 quadrillions, 100 quadrillions, quintillions. And it keeps going on and on and on and on until you get to a Google. So not the website where you search everything in your emails on, but a Google. Anyone know what a Google is? A Google is a 1 with 100 zeros past it. So it's basically 10 to the 99th. Ten to the 99th is a very big number. And so if anyone ever has a Google's worth of money, either the money is worthless or they own everything. Decimal places go in the same magnitude, but they're the denominator of the fraction. On the left-hand side, they're the numerator of the fraction. So you can think about this as like 1 over 1, 10 over 1, 100 over 1, 1,000 over 1. On the other hand, it's flipped, where this is 1 over 10, 1 over 100, 1 over 1,000, 1 over 10,000, and then 1 over 100,000. So basically, the decimal point is the dividing line between whether the growing number is the numerator or the denominator. We've already done rounding. Notice how the 3.27 that we calculated for those M&Ms earlier with the bag that the book provided. We had that 0.3272727 repeating. And we decided, oh, well, the 7 is large enough, so we round up to 0.33. So if we round to the nearest dollar for a 166.39, what will we get?
A 66.
Correct. 166. We round to the nearest penny, then we get 1196.89.
9.
Right. Rounding to the nearest hundredth, we get, which is the same as rounding to the nearest cent. We get 38.56 because the 3 is less than 5. And then we round to the nearest thousandth. We get 432.998. But you could also round to the nearest hundredth, and then this becomes 1433.00. Now, what if we want to convert things to fractions? Well, that's where this little chart is handy, because if you have a decimal, you already know, as far as the decimal goes, you know what your denominator is. So if you have 3 decimal places, you automatically know your denominator is 1,000. If you go 1, it's 10. If you go 2, it's 100. If you go 4, it's 10,000. So converting a decimal to a fraction is easy. The hard part comes from the simplification, but chances are you might not even be able to simplify it. So if you have like 33 over 1,000, well, 1,000 is not divisible by 3. 1,000 is not divisible by 6. 1,000 is not, well, neither is 33. 1,000 not divisible by 11. And it's not divisible by 33. And as a result, you end up with just 33 over 1,000. So 3/10, the decimal. If you want to convert fractions to decimal, it's easy, because if you're going decimal to fraction, it's easy because it's whatever the denominator is. If you're going from fraction to decimal, if you have 10, then it's 1 digit. If it's 100, it's 2 after the decimal. If it's 1,000, it's 3. If it's 10,000, it's 4. So we know that this is going to be 0.3, 1 place, 0.03, 2, 0.003, 3, 0.0003, 4. Just I don't want to jump ahead if people are trying to jot notes down. If you need me to go back to anything, just let me know. Now, if we want to convert a fraction to a decimal and it's not divisible by 10, 100, 1,000, or anything that's base 10 in the denominator. If it's base 10 in the denominator, then it's easy. But if it's not base 10 in the denominator, like 3/4, then we just have to use good old-fashioned long division. So I'm just going to recreate what they've already drawn. 3/4. How many times does 3 go into 4? None. So when you have decimals, what you do is you borrow a 0 and you put a decimal place there. And so you get 30. So how many times does 4 go into 30? It goes in 7 times. So 7 times 4 is 28. You're left with 2. Well, we still have a remainder. So we borrow another 0. And so how many times does 4 go into 20? 5 times. 5 times 4 is 20. We have no remainder. This is our final answer. So long division isn't so bad. You just have to remember that once you start borrowing zeros, there needs to be a decimal place. The first time you use it, you put a decimal place there. And every subsequent time you don't have to move, you just add another line to it because you've already established the decimal, you already established that you're borrowing that's less than, or it's less than a whole, because you could still have a whole number to the left of it. And you end up with this decimal value. So let's do another example with this. Let's say we have, I don't know, let's do 17. Let's do something a little bit less crazy. Let's do 9/40. Okay. Does that seem reasonable? 9/40. So we do 9 divided by 40. Well, 9 can't go into 40. Oh, before we even do that, is 9/40th, can we simplify it? No, because 40 is not divisible by 3 or 9. So we go to 9/40. We need to put a 0 here. We need to put a decimal point. We borrow the 0. We get 90. Well, 40 goes into 90 twice. 2 times 40 is 80. So we're left with 10. Can 10 go into 40? No. So we need to borrow another 0. So 100, 40 goes into 100 twice. So we get 80 again. We get 200 or 20. 20 can't go into 40, but 200 can. So how many times does 40 go into 20 or 200? 5. And 5 times 40 is 200, and we have no remainder left. So our answer is 0.225. So any questions, clarifications, concerns related to long division involving decimals?
Could you make that 0.225 into 0.23 or no?
It depends on the question. So if the question was like, okay, we're trying to convert this into like cents, well, then it would make sense, no pun intended. Well, actually that was intentional, to round it to 0.23. I would just look at the question or the specific circumstances. If you're like making like an accounting spreadsheet and you're looking at it in terms of cents, I'd round it up or down. If it's just like saying rounded the thousandth, or just find the whole decimal and solve it, assuming that there will be a point in which there's no remainder, then at that point I would do that. So like here, I would, if it was a dollar value, I'd round it. If it wasn't, I would leave it the same because you found the terminal point. But if you get something where like you've done this like 7 times and you're getting like unique numbers and it doesn't seem like it's ever gonna break out to anything, I would just round it I would stop wherever you're at and then just round it to the nearest thousandth or hundredth.
Okay, thank you.
Yep, good question. So converting mixed numbers to decimals. First step is to figure out the decimal part. Now, this is a little bit different than before, where you had to multiply the mixed number times, or the whole number times the denominator and add it. The reason why we're not doing that now is because if we did that, it would be redundant, because the first part of the problem would be to divide by 5 and you get the same whole number. So we already know that the whole number is going to be 8, because that's going to be on the left-hand side. So any whole number in a mixed number is going to be on the left-hand side of the decimal point. So the only thing we care about is this 2/5 right here. So 2/5, 2 divided by 5 can't, need to borrow the 0, so we get 20. There's a decimal point established because of the borrowing. 20 divided by 5 is 4. 4 times 5 is 20. 20 minus 20 is 0. So we get 0.4. And our final answer is 8 plus 0.4, which is 8.4. So any questions about that? Okay. So if we want to convert this to a fraction, again, remember, like I said, you know what the denominator is. If it's 0.24, you know the denominator is going to be 100 because there's two numbers after the decimal point. But if you're turning it into a fraction, the one thing I failed to mention before is that you need to treat all of the numbers after the decimal point as a whole number and make that the numerator. So the number of places will indicate the denominator. We already know it's going to be less than 1, so it's going to be a proper fraction. But the numerator is just going to be whatever the top, or whatever the number is. So in this case, this is the number is 24, so 24 goes on top. Since we have 2 places, it's going to be 100. I don't care about that step. I don't care about that step. I care about this step. If you follow that little chart, you don't even need these extra steps. You can just jump straight to the end. Put this straight up top, put this on the bottom. If you want to simplify this, you can. You can make this 12 over 50. You can actually make this 6 over 25. Any other questions about this? So if you have a mixed decimal is where you have a whole number on one side and then the decimal on the other side. To a fraction, well, you would know that it's 45 over 100 because you have 2 decimal places, so it's 100, and then you have the 45 on top. And since 17 is a whole number, that just stays as a whole number. So you would convert this to 17, which is the whole number, and then 45 over 100 is the fraction. If you wanted to make it an improper fraction, then you multiply the 17 times 100, add that to the top, and you'd be left with 1745 over 100 has the same value. Now, what if we want to add decimals? I think most of us are used to this because when you're at the grocery store and you're trying to add in like $17.50 plus $1.18 plus $2.95, you're trying to figure out what the total is or the subtotal is, or maybe you know the tax rate and you want to add in the tax and all the other stuff. You're doing this all the time, so I think you're probably comfortable with this. But if you want to add these numbers together, the most important thing about arithmetic when you're doing multiplication or addition with whole numbers or decimals is to line them up properly. So you want to make sure that 4 is a whole number. So I would put a decimal there if you know that decimals are coming. 7.3, 36.139, 0.0007, and then 8.22. That's the most important part, is to make sure that your decimal point is consistently down the line and that all of your places are consistent. So again, this is tens, ones, decimal, 1/10, 1/100, 1/1000, 1/10,000. So we add these all up. So there's nothing else in the 10,000ths column except 7, so that's what's left. 9 plus 0 in the thousands column gives you 9. 3 plus 2 in the hundreds column gives you 5. 3 plus 1 plus 2 gives you 6 in the tenths column. And then add these numbers together. 4 plus 7 is 11, plus 36 is 47, plus 8 is 55. So you're left with 55.6597, which would round to 55.66. Any questions about adding decimals? Okay. Subtracting decimals. So if we're doing 45.3 minus 15.273, just want to line up. And then again, you might have to borrow. So in this case, you got a 0 and a 0. Well, in this case, you need to borrow to the 2. This becomes a 10, then becomes a 9. This becomes a 10. This becomes 7. 9 minus 7 is 2. 2 minus 2 is 0. 30, because 45 minus 15 is 30. And then bam, you got your answer. Are we familiar with borrowing and subtraction and addition? I mean, most of us just use calculators these days, and for a problem like this, you would probably just use a calculator, but you'd be surprised how, if you become really proficient with this stuff, that it's actually quicker sometimes to do in your head than on a calculator. Because then you got to pull out your phone, open the app, type it in, all the other stuff. And I guess those lines were there for the borrowing, but I didn't line them up properly. And then something that you can always do if you have done a subtraction problem is you can always add it back. You can add whatever you were subtracting and add it to your final differential answer, and then you should get the original number. For multiplying decimals, well, first off, I wouldn't recommend, well, again, so a lot of these slides are coming from a textbook or our textbook. I converted them so that way, like, I could add my own stuff to it, but generally speaking, it's more efficient for me to use the examples that are given to me. But some of the methodology that they use could work. It does work, but I have different ways in which I do it, and you should do whichever you're comfortable with. If you're more comfortable with doing things my way, then do things my way. If you're more comfortable doing it the way the book likes it, do it that way. If you've come up with a third option that's effective, then do that. Then maybe you watch Khan Academy and you found a different way. That's okay. Though really the only goal is to make sure that you are comfortable with doing these things proficiently. So the reason why I deviate from what this book is doing is the book here is doing a process where they just treat everything as a whole number and then they add the decimal points at the end, which is what I do. But I don't like it that things are off-centered with the scale. So like notice how here like the 6.7 is offline with the 8.52. It should either be that the 8.52 and the decimal points are directly under each other, or it should be treated, if you're doing it as whole numbers, the 67 and then an 852 and have those lined up and then add in the decimal points later. It shouldn't be this weird thing in between. So we do it the book's way. What they're going to do is they're going to multiply through the 7 through the top, and then they're going to multiply the 6 through the top, and then they're going to add it together and then add in the decimal place after the fact. So if you have 2 decimals after your number, then that means that you have to move this whole number, assuming there's a dot there, over 2 spots. And then if you have a 3rd decimal place from the second number, then you need to move it over a 3rd time before you're at your final destination point for the decimal point. So for multiplying, you do 7 times 2, which is 14. 4, carry the 1. 7 times 5 is 35, plus 1 is 36, carry the 3. 7 times 8 is 56, plus 3 is 59. Cool. 6 times 2 is 12, carry the 1. 6 times 5 is 1, carry the 3. 6 times 8 is 48, plus 3 is 51. And then you have 3 decimal places, so you go over 3 spots and you're left with 57.084. For this one, 6 times 6, here at the bottom, 6 times 6 is 36, carry the 3. 6 times 3 is 18, carry the 21. 6 times 2 is 12, 14. 1 times 6 is 6, 1 times 3 is 3, 1 times 2 is 2, so you get the same, and then 0 times that is 0, so there's nothing else to add. But in this case, there's 5 decimal spots. There's 2 here, there's 3 here, so that means that even at this point of 3,776, you got to move past 5 points. So 1, 2, 3, 4. We're out of numbers, so now I got to add a 5th 0, 5. And then, so your final answer is 0.03776. So my old way was to, so in this case, if you do 8.52 times, you can either do 6.7, so it's consistent. If you're 14, 1, 13, 1, 57. I did that wrong. 7 times 5 is 35, 36. 3, 7, 8 is 59, 64. And then the standard always was to drop a 0 down because you're in a different place. But the reality is you're not, because there's no 10s here. It's actually just 1. So that's the reason why this part isn't adding that 0 that you're historically used to doing when you're like multiplying like 36 times 24, where you do 36 times 4 and then you do 36 times 20, and then you add that 0 in to accompany the 2 times 36 and then add the 0 to make it 720 instead of 72. But because your numerical values are less than 10, you don't need to add that 0 in, and in fact, you're actually going to make it smaller by adding in moving the dot over a place equivalent to every number that is listed after the decimal. Any questions about this? I know I kind of went fast with the multiplication, but that's why I said last week it might be encouraging to kind of go find like just Google search a multiplication table up to like 10 by 10 or 12 by 12 and just kind of a lot of these. The reason why this becomes doable is because you can memorize all these little relationships. Okay, 7 times 2 is 14, 7 times 9 is 35, 56, 12, 30, 48. You just know it off the top of your head, almost like it's words instead of numbers. 6 times 6 is 36, 18, 21, 12, 14. So you're just zipping through these numbers, breaking it down, then adding it, then adding the decimal after the fact. So doing a multiplication table or something of that nature might be really helpful. What about dividing decimals? As I mentioned before, in the case of borrowing creates decimals, but what if you have different decimal points? Well, the easiest way to do this is to just make things a whole number. If you make things a whole number, then you can do a traditional division problem, and then you can add in the decimals after the fact. So if you're doing 32.8 divided by 2.5, move the decimal over a space equivalent to making sure that everything is a whole number. So if 32.8 and 2.5, make it so it's 328 divided by 25, so it's an easier multiplication problem. So there you get 13 times 25 gives you 1 times 25, 7, 3 times 5, 75, 3, you get 1, 25, 5, 0, you get 2, so you get 50 over 50, which is 0. So 13.12 is your answer. So how did I get 13.12? Because you got to remember that we borrowed. So then your decimal point goes here, and then you add the two numbers after the fact. So the reason why you move over that decimal point is so it's easier for the division, because 328 divided by 25 is the same ratio as 32.8 over 2.5. So that's why you don't have to re-add the decimal back at the end. Now, if it's the other way, it might be different, but it's not. And the reason why it would be smaller in that case is because you would be borrowing immediately instead of 2 or 3 terms down the line. So the price of an Apple Watch can be bought for $700 US in Canada. So in Canada, it's 700 USD. The exchange rate is that $1 is equal to 1.2587 CAD. CAD is our abbreviation for Canadian dollars. So in order to find the answer here, you want to convert this to Canadian dollars. You're going to do 700 times 1.2587. Why are you doing that? Because it takes more Canadian dollars to make $1 US than vice versa. So we're going to be multiplying instead of dividing. 7 cycled through is 0, 0, 49. 8 times it's going to be 0, 0, 56. 0, 0, 35. Sorry about that. For some reason, I'm too close to the bottom. So we're going to do, why won't you let me work? 3,500 1,400, 700. You add all this up, and you end up with $881.09. So if you add all these numbers up, you get 4,900 plus 56, 3,500 plus 1,400 plus. I messed up that multiplication. I'm such a fool, but it's okay to make mistakes. That's the reality of life. Is I made a critical error on my own where here's the reality. The easiest way to do this is to go, okay, it's 700 plus 1 times 700 is 700. We already know it's going to be at least 700. So then we can just ignore that and then do this multiplication problem and not forget to add in the decimals at the end. So 7, let's get 4,900. You get 5,600. You get 3,500, and you get 1,400. And when you add all that residual up, you end up with 181.09. And so you end up with that final answer. Look at me trying to do long division for a problem that we should just use our calculator for. For long division, long multiplication. And so if you want to reverse engineer the answer, I think there's a table to find this relationship of 0.7945. All you would do is do 1 divided by 1.2587. That gives you 0.79447. So that means that 1 Canadian dollar is equal to 79.45 US cents. And then $1 is equal to $1.2587 Canadian. As I mentioned before, the shortcut for multiplication is if it's by a multiple of 10, all you got to do is move in one direction or the other. If you're multiplying by a whole number, you move the decimal point to the right. So by 10, you move it over once. By 100, you move it over twice. By 1,000, you move it over 3 times. For division, you move in the opposite direction. If you're dividing by 10, you move to the left 1. If you're dividing by 100, you move to the left twice. Dividing by 1,000, move to the left 3 times. Dividing by 10,000, moving to the left 4 times. And if you're ever confused, just go back to that good old-fashioned fraction table in the beginning of the slide deck. So the problem says around 75.9913 as indicated. So if we run around to the nearest tenth, what's it going to be? This one's a little tricky because if you're at 75.99, this indicates to round up. So you would round this to 10. Well, that means that this becomes a 0, and then you add a 1 to this, so this becomes 6. So when you round to the nearest tenth, you're actually getting 76.0. When you round to the nearest hundredth, you round down because of the 1, so you're at 75.99. Whoops. And then when you're in thousandths, then you have that 1, 3 says to round down, so you're at 75.991. By the way, this is a typo that I didn't make. That should be a 5, not a 6. Any questions? I don't want you to feel like you're overwhelmed or rushed or anything like that. I just want to know if you're comfortable, and if you're not, well, go over more. So problem 316 says to convert this into a decimal. Well, if you're in a thousands territory, you know that there's going to be 0 point blank blank blank. And if there's happens to be 3 numbers, then it's just 979. If you want to round to the nearest hundredth, well, this suggests round up, and then you're at 0.98. Convert this to a fraction. Well, and it says don't reduce. Well, you know, if there's 3 decimal spots, then you go to 1,000, turn this to a whole number. It's 825 over 1,000, which is sitting right there at the bottom. If you wanted to simplify it, you could. You could divide it by 5. You would, if you divided it by 5, you'd be at 200 in the bottom, and you'd be at 85. No, 20 times 165 on the top. Could that be divided again? Yes. This would be 40. And this would be 65 times 15, 13, 33. Can this be broken down? I don't think so. So if you wanted to simplify, it would be 33 over 40, but really the exercise is to remember those shortcuts, and knowing that 3 decimal places implies that there's 1,000. Convert this to a mixed number. Well, remember it's 48 over 100. And then this is 28. That's what you get here. If you wanted to reduce it, it would be 28 and 12 over 25. Jill Horn went to Japan and bought an animation cell of SpongeBob. The price was 25,000 yen. What is the price in US dollars? I don't know, because I don't know what the exchange rate is. But apparently the exchange rate is that 25,000 yen, or excuse me, 1 yen is equal to 9/10 of a cent. So if you multiply 25,000 times 0.009087, you end up with $227.18. And then this is the reverse scale. So if you do 1 divided by 0.009087, you would actually get that $1 is equal to 110.05 yen. That's it. That's decimals. Does anybody have any questions about decimals, how to work with them, how to multiply them, how to divide them? I know we have calculators and stuff that allow for us to do a lot of this stuff, but knowing the basic fundamentals of how to solve it can really help you in a pinch and help expedite understanding of these things as we start digging into things a little bit more. So
I have a question. So on the like exams,
Mhm.
will we have to show our like the how we divided it or multiplied it, or is it just going to be the answer?
for the like the main exam or the chapter quiz.
The main exam.
So for the main exam, it's just going to be answers for the sake of efficiency, but I haven't wrote it yet, so I'll let you know next week what I want, because I could do it where you basically have like a essay block to like type in justifications and show your work and stuff like that. What I might do as a substitute for the sake of efficiency is what I'll do is you'll take the main exam and you'll just type in your answers and mark true, false, and mark your multiple choice answers. But when you submit it, within like an hour, if possible, if you have scratch work that you're doing on the side in a notebook, take a picture of that and upload it. So that way, when I grade it, I can give you partial credit for things that you don't get right based on where you were headed with the problem. I think that's a good solution. It keeps it so you can get feedback quicker. So I don't have to grade everything before you see what you got right and what you got wrong after the deadline. And then secondly, allows for me to give you some credit back based on effort and understanding. So it's a good question. I'll finalize that next week once I got the exam written and know what we're going to cover by then. But I would guess that that's probably what I'm going to do.
Thank you.
You're welcome. Does anybody have any other questions?